Hey guys, this is Mr. Barthold, and this is the video I said I was going to do on free fall. What I've decided to do is, I know that y'all have seen this, this material already last year, and so I figure I could just present y'all, 3 or 4 problems, and we can talk about how to work through the problems, and that should refresh what you've learned in the past. And yeah, so. We'll start with the most basic free fall problem you can have, and that is, you're holding something or something is at rest, and then whatever holds it stops holding it. So you drop it, or it falls off or whatnot, and at that point it is in free fall. Only gravity is acting upon it. All right. Important thing to remember is that free fall is just another form of constant acceleration. When only gravity is acting on it, it is gravity. Gravity itself, g equals 9.8 meters per second squared, or that is the acceleration of gravity, and it is constant. It is always the same. All right. And so these 4 equations, which are found in chapter 2 in your book, will be handy. So, how do we go about solving one of these? We just have to remember some basic assumptions. All right. So let's say, or I drew a little. Let's say you're standing on something that's 3 meters tall, and you drop a ball, so this height is 3 meters. All right, and so a very, very common question is, how long does it take to hit the ground? All right, so the question we're going to be looking at is to find the time it takes to hit the ground. Find t that it takes to hit the ground. I know some of y'all are asking about the guess method. That is definitely a good method of working out problems. All right. So in a free fall situation, what are we given? We are given definitely given the height. All right, and so what is that height? That is going to be our delta y. That is our change in vertical position. So you can use delta x or delta y. Y is typically for vertical, and delta y in this case would be -3 meters. Why is that? It starts at the top and it ends at the bottom. So a sign convention that you definitely should adopt. Free fall, we say g is equal to -9.8 meters per second squared. And the negative sign is there because it is falling downwards. And so we typically say that downwards is the negative direction. If this was, x-y axis, up would be positive y, down would be negative y. And so if it is falling downwards, it's going to lose 3 meters. Another way to think about it is, let's say we define where it starts from as 0, our origin. Our initial position in the y direction would be 0. Our final position, whenever it hits the ground, so y final would be 3 meters below, or -3, and so delta y, y minus y naught, -3 minus 0 is -3. All right, so just kind of the sign convention. If you're going to be using g as -9.8, you're going to want the position to be, or the displacement to be negative as well if it's falling downwards. A very common assumption, especially when you are dropping things, is that your initial velocity, right? Your vertical velocity, if it is being dropped, it is not being thrown down or thrown up, so it is not given any initial velocity. So the initial vertical velocity is going to be 0. And that's going to make our equation pretty easy to solve. And so we know the positions, we know that we're dropping it. The last thing that we always know in free fall is the acceleration, which is going to be -9.8 meters per second squared. All right, so we're looking for, in this case, we're looking for the time it takes to hit the ground. So time to hit ground. And what can we use? A quick look at our equations, and will let us know that we can use this one. This initial velocity will cancel out. So we know the change of position, we know acceleration, we can just solve for time. This is definitely one of the most useful equations, the second one right here. All right, so y, I'm just going to change it from x to y because we're doing vertical motion, plus initial velocity time, plus 1/2 at squared. if it's vertical, I could even just say this is g, because the acceleration is g vertically, right? We substitute that in, and this is very simple to solve. I'll go ahead and substitute the actual. So this would be -3 equal meters. Let's not get lazy. Equals 0. I'll leave that out. Plus the initial velocity is 0. So 1/2 g -9.8 meters per second squared times squared. Half of that is 4.9. So we'll see that t squared is -3 meters divided by -4.9 meters per second squared. And so you can take the square root of that to find what t should be equal to, right? T is equal, I don't have my calculator, sorry about that. So we have 3/4.9, that should be 0.612, and the square root of that is 0.78, 782 and whatnot, so the time is going to be 0.78 seconds. Alright, so remember, common assumptions. Well, first off, in free fall acceleration, always -9.8. The initial velocity, if it is being dropped or even thrown horizontally, right? There's no initial vertical velocity, and so the initial velocity in the y direction is 0. And then change position. Remember the sign convention. It is possible to say that it falls positive 3 meters and use acceleration as positive, but I would caution against that, because there are times when the ball will be thrown upwards or thrown downwards, and you're really going to want to use positive and negative consistently just to build a good habit. All right, that's just my recommendation. Okay, so that's basic problem. Another very common problem is, what if the ball is thrown upwards? How long is it going to be in the air, or what is the maximum height that it can attain? So let's turn the page here. Make sure you can see this. Let's do a second problem. And let's say that now we're going to throw the ball upwards. So a ball is thrown upwards, and we're still doing it with one dimension. So it's thrown straight upwards. We're not going to mess with angles quite yet. So it's thrown straight upwards at a speed of or we can say we'll say speed of let's go with 3 again. This time it's a speed, so 3 meters per second. And we'll answer the two questions that I just asked. So the first part is going to be how high will it go, or what's the maximum height that it can obtain. So how high will it go? And the second question will be, how long is it in the air? Two very, very common questions. Hope my pen does not go out on me here. So how long is it in the air? All right, first, so to start with this, I will draw a few graphs just to kind of make sure we understand, kind of tie this into the graphing the motion. 3 graphs. It's going to be distance, position. I'm going to say y, vertical position, velocity, and acceleration. And so what do we have? A ball is thrown upwards at a speed of 3. So what's going to happen? The acceleration, again, once it is thrown up, it is in free fall. The acceleration is -9.8. So I probably should have, let's go ahead and make this our 0 axis. And our acceleration is constant down here at -9.8. Alright, kind of cheated there. Make sure I'm straight here. Alright, so the acceleration is constant, -9.8. Awesome. What's the velocity looking like? Alright, this one's kind of tricky. We will need to extend our graph a little bit. First off, the position, I'm sure y'all can, that one's pretty straightforward, right? Let's say you're throwing it, you're starting from the ground, it gets thrown upwards, and then it comes back down, right? So we're starting with, it's thrown upwards, and then it reaches some maximum height, and then it starts to come back down. It's going to look something like that. All right, so thrown up, and I mean, the ball itself is just going to go straight up and straight down, but whenever you add time here, it's going up with time and then back down with time as well. So So the velocity, what's going on? A few ways you can think about it. First, I mean, it is thrown up, so it is thrown with a positive velocity because it is thrown upwards, and it's at 3. So initial velocity is going to be 3. That velocity will be decreasing at a rate of 9.8 meters per second. And so our graph is going to be looking something like this. So what's happening? It starts with an initial positive velocity. When it crosses the axis here, the velocity is 0, right? So that means that this is where it's at rest, at the top. It goes up, it stops at the top with the velocity of 0, and then it comes back down and it has a negative velocity. And in actuality, it is symmetric. So when it comes back down, it will have a velocity of -3. All right. Things in the air have, or projectiles in themselves, projectile motion is inherently symmetric. So that is a handy tidbit that we're going to exploit one more time. All right. So how high will it go? Let's go ahead and work on that. What do we know? We know that it was thrown up with an initial velocity of 3 meters per second. So that is +3, while the acceleration is -9.8 meters per second squared. Notice it is possible to have a positive velocity and a negative acceleration. That is a common misconception. So you can have a negative and a negative, positive, I mean it can be any sign. And actually, a little trick is that if these signs are the same, then that means that it would be increasing its speed. If the signs are different, then it would be decreasing speed. So in this case, it's thrown upwards with a positive velocity, has a negative acceleration. That means it's going to be slowing down. And then once it starts going back down, it will have a negative velocity and a negative acceleration, so it will actually be speeding up. So if these signs are the same, it's speeding up. If the signs are different, it is slowing down. So that's actually an interesting little tidbit. So how are we going to go about solving this? There is one of our handy equations can do this all in one fell swoop. And which one is it? What do we think? There's one assumption that we need to make. So similarly, on the last one, we assume that when you drop it, the initial velocity is 0. Likewise, whenever it reaches its highest point, we know that the velocity is 0 as well. So we can say that, I forgot my initial here. Initial velocity is +3. And we want to know how high will it go. Well, at the highest point, the final velocity will be 0. All right, and we are looking for the height. So we are looking for we also know the initial position is 0, right? And so we're looking for the final position. This will be our unknown as meters. All right, so a quick look, and I used D again. That's such a bad habit. I'm sorry. Why and why not? And so our third equation here, we know the velocities, we know the acceleration, and we're trying to find that change in distance. So our final velocity is equal to our initial velocity squared is equal to our initial velocity squared plus 2 acceleration delta y, or y minus y naught. And so we can substitute our numbers in. Final velocity is 0. Initial velocity is +3. We are going to square these numbers. Plus 2 acceleration, -9.8, times delta y. So y, which is what we're looking for, minus the initial, which is 0. So just y. Solve that out. We can subtract this over, so we have -9 meters squared per second squared equals 2 times that is -19.6 meters per second squared times y. And so y will just be -9 divided by -19.6. This should be 0.46. So 0.46, the units check out. They do, right? We're going to divide by seconds squared, and one of the meters will divide away. So we are left with a meter. So 0.46 meters. Notice it is positive. All the sign convention has worked out. It is thrown upwards. We're good to go. For part B, we can find the time that it took to get to the top. We can do that a few different ways. The easiest way is to use just the very first equation here. All right, so the final velocity is the initial velocity plus acceleration time. 0 equals 3 meters per second plus acceleration times time. And so time is, doing the algebra, -3 divided by -9.8 meters per second squared. This is 0.31. I have a real calculator, I just don't have it with me today, so I'm scooching over to my computer, sorry about that. To three significant figures, we're at 0.306 seconds. Alright, so now you're probably already thinking that this is the time that it takes for it to, whenever you first threw it, to the time it takes to get to the top. The question is, how long was it in the air? Alright, and so this is where we're going to exploit the symmetry again. This motion especially, since it's starting at the ground and ending at the ground, it is symmetric. And so if it takes 0.306 seconds to get to the top of its motion, it will take 0.306 seconds to get to the bottom of its motion. Alright, and so the total time, so t total, will be 2 times that, which will be 612.612 seconds. Alright, so those are the two very basic projectile motion problems: something being dropped, something being thrown in the air. Remember, common assumptions: when things are at the top of its trajectory, whenever it is thrown, or anytime it's going up and back down, at the top the velocity is 0. When something is dropped, the velocity is 0 initially. The acceleration is always -9.8, and remember your sign conventions, right? And if you're consistent with all of that, you'll find these problems to be rather simple. I'm going to do one more video with with a few, I guess, more difficult problems. One of them will involve the quadratic equation, and another one is just it's just pretty tricky. All right, so I encourage you all to watch that one as well.